does it work? Yep, it should work. And yeah, so you can see the preview there. So welcome back from lunch, everyone. We lost a couple people in person, but that's all right. So the next speaker is going to be from Siemens, and you have a whole plethora of presenters, it feels like. So I'll just let you guys kind of discuss it and move on to our first presentation of the afternoon.
Hello, everyone. Yeah, nice to meet you again. I see some familiar names online as well that are joining this meeting. Yeah, so today's presentation is about the user interaction with digital twins, and Emilio will have a nice introduction part on that, and also some use cases, and then additional 2 use cases from myself and Claudio as well towards the end. So this is a bit the agenda of our talk. First, yeah, Emilio will introduce our work on executable digital twins. Then he will talk about these case studies of wind turbine blades. And then I will go into a fancy topic called direct field acoustic excitation. Some of you may know what it is, some of you not, but I will give a brief introduction on that. And then Claudio at the end will join us remotely and present the virtual sound simulator. So I think with that, I will leave the microphone to Emilio.
Hopefully that's good enough to hear. So hello everyone. Yeah, I'm Emilio Di Lorenzo, and I do work for Siemens since about 10 years. And yeah, today I will be presenting a bit the introduction on the XDT, and then this example that we had together with ETU about having a digital twin in place for a wind turbine blade. So just a brief history of let's say the part of Siemens in which we are involved. So as you can see from this slide, that's the company has been going through a lot of different acquisitions. So it's basically a bunch of more than 10 companies put together. They started in 2007, but where we come in the picture is this LMS logo that some of you might know. So that's the company based in Belgium, in Leuven. That's Leuven Measurement System, and that was acquired back in 2012. Actually, that was exactly the same year when I joined the company. And now we've been going through other acquisitions, and then the company is enlarging with the same vision. At the end, the main vision is to bring together all these technologies that you see in this slide. So on one side we have the test, which is the division in which both Mattia, myself, and Claudio we are working on. But then there are other people working on simulation data, CFD, 3D simulation, geometry, and so on. And the objective is then to bring all of these together in our division, which is now simulation and test solutions within the Siemens digital industries. And there, indeed, the idea is to go for predictive engineering analytics. So bringing all this together, the pieces of the puzzle, in order to build a conceptual model made up of both simulation and test. And that's where the definition of digital twin fits very well. And actually, in the past years, we've been working a lot on finding, let's say, proper definition. And that's, I would call it the Siemens definition of the executable digital twin that you see here on this slide. And there are a bit of sentences on what is this about. So this should be working starting from the design to the production to the in-service phase. So all these 3 pieces should come together. So the executable digital twin should be, let's say, in action all along this cycle. So along the product life cycle. And then this is a precise virtual representation of a physical product or process. This could be. And then this is an evolving object. That's very important. So this needs to be, let's say, continuously updated all along the life cycle. Yeah, also the last bullet points is quite important. So it's a closed loop, which provides the bidirectional connectivity between the physical asset and its virtual representation. Then in the next slide, this becomes a bit more clear. So we go with only 2 bullet points. So we reduce a bit the definition. But then what we mean with the executable digital twin is basically you can see it like an exe file. So it's a self-contained executable, which represents the digital behavior of the asset that you're gonna simulate or test. And this can be leveraged at any point in the life cycle. And then you can have a lot of different activities around it. You can have edge computing, cloud computing, and yeah, leveraging AI, model order reduction. It's quite important to have it up and running in real time. And all of this. I think this slide concludes a bit the description of the XDT, so to frame it a bit and then to make it a bit clearer all along the presentation. So both what I will present, but also Mattia and Claudio will be, let's say, working or presenting their work around this. So the physical assets needs to be reduced. You need to have a reduced order model, which can be, well, a 3D based, CFD, 1D, or even test or data-driven approaches are under investigation. And then this is packaged by using kind of standard platforms. In this case, we will use, you will see it in the next slides, this FMU concept, the functional mockup unit interface. And then this can be deployed. This can be on a physical device, an edge device, or a model-based testing, or on the cloud. That's also a possibility. Here you see an example that the colleagues have been working on in the lab. You also see this robot arm. We've been seeing something similar before in the morning. And now you will see a short movie in which you will see also the augmented reality on this tablet that the colleague is having there. So you see the robot arm pushing on a certain plate, and then you will see this coloring. And this is based on the FE model, which is running behind. So this is the stress and strain maps that you can plot on the structure and looking at it in real time. So that's both a combination of hardware and software, and both a combination of test data and simulation data. Then you see some strain gauges here on top of the plate, and this is all based on these measurements running in real time together with the FE model of the plate itself. And then you will see in the next slides with the example that we've been doing in the wind energy domain. So we've been working with in a couple of projects, Danish funded projects together with ETU Wind Energy in Denmark. And then the objective is to exactly represent what I showed in the previous video on a wind turbine blade. Then also here I recap what I just said before. So the digital twin, the executable digital twin goes along the three stages. So the ideation, so the digital product twin, then the realization of the asset, and this is the digital production twin, and finally its usage in the field. So this is the digital performance twin. And then we have a set of products at Siemens, of course, that they allow to tackle many challenges, and so from the system performance and controls to the detailed engineering with the noise and vibration, which is, let's say, our cup of tea as former LMS international company. Reliability is also important, aerodynamic performances with all these CFD tools that we have in-house right now. And then what you see there on the right of your screen, on the screen, is the Sim Center wheel. That's what we call. So this is the trademark of Siemens. All the products which fits in the digital industry software solution, they are now rebranded as Sim Center. And then here they fit both the system simulation, the CAE simulation, and the physical testing, how we call it right now. Then here I have a couple of examples that I wanted to share with you today. So this is, first I will start with this gearbox. I will have a few slides from the colleagues from our services groups, the engineering services in Leuven. They had a quite nice and interesting project on wind turbine gearbox to assess the remaining useful lifetime of those gearboxes with the Winergy. That's a German company. So here the idea is to represent each single gearbox, and then to be able then to predict which component or which, let's say, subcomponent is going to fail. And what they did was indeed to use the MindSphere platform, which is part of our Siemens solution as well, to drop all the data in the cloud. So they were monitoring a lot of turbines. It was 78. And then they were using this SCADA data to follow up the condition of these wind turbines along 1 year. I think it was the time frame they were recording. And then on the other hand, they were modeling each single gearbox in our tools, in the 3D multi-body simulation tools, in order to simulate many load cases, in order to estimate finally the lifetime of gears and bearings, which are a few of the components which are more prone to failure. And they were training also neural networks. There was a bit of machine learning on the other side. I will not go into detail on this, but it was just to share with you a bit the concept and how this is applied in real life, because this is a commercial example that was done together with the colleagues from Winergy on these gearboxes. And then here you see that the loads were all collected, the load capacity and the design lifetime was also one of the inputs to the digital twin. And each gearbox was modeled. That's also important, that the model needs to be, cannot be a single model for all the gearboxes, but they all have their own different behavior. And then finally, they were able to establish which component was going to fail. And this was a quite successful project that was released finally a couple of years ago. Now we'll move to the research phase that we are working together with DTU on this executable digital twin. So this slide is a bit an introduction slide that I've been preparing in the past to present this project in order to get it approved. So the main challenge there, it was to improve the accuracy of durability testing on composite blades. So these blades, as you see here, we're talking about 15 meters long to 14 meters long blades, which they undergo this fatigue testing, and this lasts quite a long period. And they rely only on few physical sensors. They install some strain gauges on the blades, and then they pretend then they want to assess the lifetime of the structure. And what we do here, so the solution that we provide is to combine a few physical sensor instrumentation with the smart virtual sensors, which means combining the sensor with the model in order to be able to have the full field description of the structure all along this test. And of course, as benefits that you see here on the right part of the slides, then you see that you can detect, you can measure more location. So we say we can measure the unmeasurable. And then this allows then, based on reducing the instrumentation time on one side and then expanding the strain measurements on the other side. And then you will see a bit of results later on along the presentation. Before that, I will frame it a bit in the context of these research projects, which needs to be acknowledged, of course. So that's one of them is named Reliablade. And this is a Danish funded project. All the partners are listed here on the right side. So all the big players are there, LM, Vestas, Siemens, and so on. And we are also involved as a Belgian company, but still we were able to be part of this, which is quite interesting. And here they are building actually a few blades at the DTU. So they have also a manufacturing site, and they implement also the simulation model. They have a very accurate FE of the blade, and then they are also implementing defects, artificially induced defects in the manufacturing phase. And so the idea is to perform on one side virtual testing, so the digital part, on the other side the physical testing in the lab. That's what we've also been doing in the past period. So that's a bit of the time frame. This was a bit postponed due to COVID, so this go a bit further in the future. But the idea is to perform full-scale testing in the lab and having SHM systems deployed in a laboratory environment where fatigue testing is happening. And then recently we've also been applying for a new project, which was just approved end of last year. And here the name of the project is Blatig. Other partners are involved still from the wind domain. You see also there all the icons on the right side. Here our main work is on this point, so the efficient digital image correlation. I also have a slide later on this. Basically what we do is measuring with cameras, replacing the sensors by using cameras and having a full field description of the structure, so without any contact sensors applied on it. And this is also the objective, with the objective then to have to determine the strain field and eventually damages on the structure. Here the same blades will be used also along this project. So it's the facility where we've been working in Denmark. Maybe you've seen that in your career. So they have a quite large test stand. They have 3 of them. So the large blades that you see there, the small one can be around 15 meters. The largest one, it goes above the 30 meters. I think it's 40, the max length that they can handle in the lab. So it's quite substantial, but still the blades nowadays, they are going above 100 meters. So I've been seeing the facility of Siemens Gamesa in Denmark. It's double size of this. So it's really impressive what they can do there. And here you see the test that has been, the fatigue test running on this about 15 meters blade on this test stand. And then here a bit what is needed by the certification. So there are standards for wind turbine blade certifications. And all these blades, they need to undergo static test, fatigue test, and also dynamic test, which are quite limited. Only a few modes needs to be identified by certification. But still, what we want to prove is also that with the same instrumentation, we can cover the three of them. So having the same strain gauge instrumentation or a camera-based instrumentation, we are able also to determine the dynamic characteristic of the blade by using, for example, here I have a slide on strain-based operational model analysis. So our company is quite well known for this, the model analysis capabilities. So we do have this Polymax to identify the modes. In this case, we go operational, so we don't know the input. The structure is running continuously, and then we use the operational model analysis. And moreover, we don't look at classical accelerometers based measurements, but we look at strain gauges. And then we were able, indeed, in this case, to identify most of the modes we were interested in, because the frequency range is pretty low, and then strain gauges were enough to cover such a frequency range. And then we are able also to plot, that's what you see here on the bottom left, the strain mode shapes, which identify where the higher strains are in the structure. And then we extended this by using digital image correlation, as I just said a few minutes ago. So here, what we do is we look at the structure with two cameras. We need to apply this speckle pattern that you see on the picture. So the structure needs to be black and white. That's a bit one of the requirements of these camera-based techniques. What we are able to get out of that is the full field geometry. So that's already a nice step, that we are able to reconstruct the geometry by just looking at it. And then on top of that, we get thousands of sensors, both from can be displacement sensors and then accelerations, or also strains are automatically detected having such a fine grid of measurements. And then in this case, you see the first two modes of the blade fully reconstructed by experimental campaign by using cameras. And I also have a slide at the end of my part where I will show this on a 30 meters blade undergoing fatigue testing. But then I will make a step back now. So we went back to the lab, and we decided that we needed to have some in-house demonstrators. And that's what you see here on this slide. So we have two physical demonstrators in the lab now at Siemens. And the first one is a 3D printed scaled wind turbine blade. So it's a bit a fancy example. You see the 4 parts in which it was built by 3D Systems, a company based in Flanders as well, in Belgium. And then it was polished, and then we have a quite nice shape blade. So the design here comes from DTU. That's the same blade that you saw in the previous picture. It was downscaled 10:1, and then we printed it in titanium in this case. While on the right side, you have the composite version. So this was manufactured at the DTU. It's exactly the same blade, but it's in glass fiber. And then you see here some tests that we are doing. We also speckled this one. We did, again, DIC on this blade. And I will show a bit the activities around this. So here you see how the blade looked like when we printed it. Then it was polished, and then it became super nice and super clean. And then you see here the airfoil, basically, on the. So in this case, of course, that's not a real blade. The normal blade, they have, as you will see later on, internal structures to support it. In this case, we only had the external shape to be the same as the real blades, let's say. And this was a bit to run some experimental campaigns in-house to perform this virtual sensing exercise in order to enlarge the representation. Then here you see some results. I will not go into details of this. But the main idea is that, I wanted to show that we did quite some experiments, both hammer testing, shaker testing. Here you see a fancy pull and release testing in the middle, where we were hanging masses and then just cutting the rope and then let the blade vibrate. And then here on these plots, they show a bit about the input estimation. So here the blue and the cyan curves, they are basically on top of each other. On one side, we see the measurement results of the input, so the force cell that it was installed. On the other side, you see the estimated quantities, both in the time domain on top and the frequency domain on the bottom part. On the bottom plots, on the other end, you see the response estimation on all the sensors that were installed. So here we were able to reproduce quite well the full field. And then you will see in this example that we did last year at Series in Belgium. It was a masterclass where we delivered our, was not starting. We delivered our blade. Sorry for that. Messed it up. Voila. Well, the second video is not starting, but anyhow, here you see the blade hanged on this, and then now you will see on the tablet a bit what I wanted to show. So the video is a bit moving bit too much. But overall, yeah, here you see the blade and it's physical, and the digital twin of the blade itself is also there. Now the guy will be pushing on the tip of the blade, and then you will see that the strain field will be, yeah, here it's not very visible in this. Yeah, here you see it a bit more. So here we are plotting the strain field on top of the real structure. So we were able to align the two structures, the physical and the digital twin, and then we were able to reconstruct the full field based on a few strain gauges that were installed on the blade. Yeah, you can spot them on the top surface of the blade. And then we were able real time then to track this. So here you see the equipment that we used, and then there's an IPC being able to combine the FMU, so the packet FE model with the test data. Normally on the other movie you should see, but it's not working. Oh, yeah, maybe now it is. The comparison of the physical sensors with respect to the virtual sensors. So at a certain point there will be a plot which shows one of the strain gauges which is estimated, and the same which is measured, and they are on top of each other. So this meant that is for these cantilever like structures, it was quite straightforward then to determine the entire representation, and then look at the critical points, which of course in this case were on the root of the blade. And then this, we also did it on the large blade. You will see it later along this presentation. So this is the other demonstrator. So in this case, we have 3 blades. So the full small rotating wind turbine, it's about a couple of meters high, and with blades which are about 1.5 meters each. And then we are working, we are running quite some master thesis on it. So we have students providing on one side, improving the FE models. On the other side, building multi-body models of the entire system. On the other side, also looking into automated model analysis and damage detection using autoencoders to get damages, which in our case, we are simulating damages by adding masses. But it's one of the ideas is to introduce delamination into these composite blades. And then here you also see some results on the comparison between DIC, so camera-based measurement with accelerations. And then here you see the reconstruction of the full field shapes of the blade by using cameras and comparison with the FE model. I think I will skip this. It's about the improvement of the model itself. Here you see some tests that we did in the lab. It's not loading the picture. Some pictures are missing apparently. But yeah, and that's a bit what we did on the other end at DTU. In this case, we had also the movie is not playing, but we had the we had the full blade there, 12.6 meters blade installed with the many strain gauges on it, and then a few of them we measured with our measurement system, the SCADAs, and then a few of them were used, so only 4 of them for the estimation in the augmented Kalman filter, which is running behind all this. And then we did quite some tests. And that's a bit the movies are not playing, but anyhow, I don't know what I did. Yeah, here it's a bit the scheme so that we used. So in the center you can see this the bottom left block. So the SimCenter test lab RT, the real-time solution that we are providing, and this XDT, so the executable digital twin, is sitting here. So it's created through the simulation environment, the FE model, through SimCenter 3D, and then it's deployed on this platform. And then it's running real time together with the measurements. Measurements are coming with the classical SCADAs. You see these big pictures of strain gauges on the blade. And then the two things are combined together. And then we have the augmented reality visualization. This should have been a movie where you see the blade moving in the tablet. And then at the same time, we also get some physical data that we can further analyze in our test lab Neo platform. And I think in the next slide, it also, again, it's a movie missing, sorry for that. And here you could see that it's indeed operating in real time, the XDT of the blade, and the results are estimated and they are streamed to the cloud. So to this web UI, which is the platform, the TestLab RT platform. And then we have, normally here is a blank screen, but you have an AR visualization. So the plot is visualized on top of the blade, its strain field or displacement field. I think I need to do something to be able to show these movies. yeah, here it seems that it works. Oh, you are still able to see it online. But here, that's a demonstration that we did back in November at before EDTU. So this the right videos you see here, the plot of the displacement fields and then the strain fields on top of the surface. And then on the other movie, you see the conference that we've been attending, where we demonstrated this. That was in November at the Wind Europe Electric City Conference. And here you see the Crown Prince of Denmark as well, sitting on the blade. And here you see this is one of the professors at DTU, and that's the prince sitting on top of the blade. But then here the idea it was to demonstrate in practice that we were able to reconstruct the full field shape, and then to show this real time on the augmented reality platform. Now I will go quickly if it runs. That's a short movie that they recorded during the conference.
I think one of the exciting things with this project is this vision we have that you have the physical world and you have a digital representation of what's going on in the physical world, and that gives a lot of new opportunities to really understand blade and monitor blade, even if you are on a far away from the blade.
So this is what we call executable digital twin, and we are able to build it through our smart virtual sensing tool. It basically means that we are measuring the response of the structure with just a couple of physical sensors, and then we are processing this data together with a model, and by coupling this information, we are able to get the full field response of the structure, in this case of a wind turbine blade.
So here we have our measurement system, so the SCADAs, which is equipped with test lab, and it's measuring several strain gauges along the blade. On top of that, we have an FE model, which is running, and then that you see it there real-time updated. While the blade is oscillating, you see the full field strain map and displacement map as well, which is based on the few sensors which we are measuring. This will allow on the longer term to reduce the number of sensors that we need to put on blades along the fatigue testing, for example, in the DTU lab. That's one of them.
If you have damage evolving in the blade, you want to know it. You can imagine that if this blade is sitting on a turbine offshore, far away from shore, then there's nobody there to see what's going on. But if you have a digital twin that follow what's happening to the blade in the center where you are overviewing the turbines, then you can use the digital twin to understand if something happened, if there's a crack or some defects that is evolving, and you can take actions before it becomes critical.
As you could see, this was quite well attended conference. It was pretty impressive, and we got attracted a lot of people there because it was a physical demonstrator being seated in the main hall. But still, there's quite some work to do. Now we just demonstrated the concept, and everything is up and running. But now we will deliver the system at DTU. So the plan is to extend this towards damage detection. Here you see an example on the left side. I hope the movie is visible also online. But it's quite impressive to see how these blades are deforming. And this is a kind of a biaxial fatigue test, which is undergoing there at DTU on these blades. And then they introduced some defects. Hopefully the movies will also work here. Not sure if you can appreciate it, but there are some induced defects. So the lamination at the trailing gauge here, again, debonding that is around this area. Hopefully you will be able to capture it with the naked eye, and some wrinkles which were induced during the manufacturing. And then we are working together with the colleagues at DTU on some vibration-based SHM, and then based on machine learning models and so on, being able to use both the model and the physical structure. Then to conclude this, I will come back to the DIC. I mentioned it before. This is also not running. So we installed quite some cameras there. There are at the end 14 pairs of cameras. So it's a joint project that we have together also with the University of Warsaw in Poland, and with DTU again. And then with the idea to be able to track, to cover a certain span of the blade, and being able to track the strain map by using cameras instead of using physical sensors. We got some preliminary results, which of course are not visible. I will show this like this. And yeah, so they're running these fatigue cycles. So you see the top left is with the reduced loads. So the load is 30% of the nominal load, and they run a few thousand cycles. In this case, it's 5,000 cycles. You see the sign behavior that is there, and then you see the strain map by using a pair of cameras. And now we are working to combine different fields of view in order to be able to get a full field representation by combining different cameras field of view. On the bottom part, you see the picture, the same points measured while the load is 100%. And then we already see the damage initiation. Of course, we knew it was there. Then we were really looking at that area. We knew that this debonding, the spark gap and the shear web was initiating at that location. And now what we are doing in these days is tracking this all along this fatigue cycle. So they are still running, we run millions of cycles, and then normally we should see this damage progressing along this. So what I presented, of course, it's a work, it's a joint effort with many colleagues from both companies, so from Siemens and from DTU. So it's very important to acknowledge all of them. And this project will continue again for 1.5 years. So yeah, hopefully some new results to come in the future. And now I will leave the word to the other colleagues. So first, Mattia, it's a physical twin, is present here, and then Claudia as a digital twin online should be joining.
Thanks a lot, Emilio. Let me just click the mic on myself. Okay, hope you can hear me. You can hear me all right. Okay, DFACS, direct field acoustic excitation. I don't know if you already know what it is. So we'll give a little bit of context before we move on to actually how we use a digital twin and how we interact with this digital twin for this DFACS application. I'm presenting, but actually the work has been done by my colleagues Alberto and Mariano in the past few years. So credits to them. You can already see a snapshot of what DFACS is in the picture in the background here. So as you can see, there is a satellite in the middle, a few microphone stands with some actual microphones on top, and then a lot of loudspeakers around. And then, yeah, I will explain now in a second what it is. So what's the idea? Let me see. Oh, okay, there's a bit of animation, so let me just put everything on. There you go. So we want to launch a satellite into space, but this satellite, is it actually going to survive the launch? Well, we don't know if we don't test it. And we don't want to end up having a satellite running around in space and not be of use, let's say, if it is broken during launch. So of course, you know, during the launch, we have engine and booster ignition and combustion at the beginning, which means that we have a lot of thermal kind of excitation, let's say, or thermal temperature increase of the rockets. So our satellite has to survive high temperatures first. And then, of course, there are other acoustic and structural type of excitations that our satellite has to survive. So we'll come back with the structural ones at the end of the presentation, but now I want to focus on the acoustic ones. Of course, when we launch the satellite, the rocket is going to generate a lot of noise, which is going to directly affect the satellite inside the rocket itself, and also indirectly by impinging and reflective jet noise. We have very high acoustic loading, as you can see here, up to 130, 145 dBs inside the launcher. And of course, we have there are standards and there are requirements from each launcher. Let's say you have here, for example, the standards for SpaceX and the Ariane 6, for example. So how do we test it? Yeah, there seems to be problems with the figures here. So let me now the displays. Now. Yeah, probably. I stopped sharing for a second. I start share again. Maybe I share the screen. That's I think it's just an issue with the. Okay, whatever. On the left, it was the picture of a reverberant chamber, which is a nice room, a green color with very hard walls, not symmetric at all. It has to be this unparalleled and uneven surfaces, but very hard. And you have your satellite. Actually, in this case, is an antenna reflector, the dish that you see in the picture on the right, basically in the middle, and you have all these microphones around. And in a reverberant field acoustic chamber, basically what happens is that you have some horns that are going to generate very loud noise. And in this case, you are going to replicate, let's say, the same acoustic excitation that the satellite dish, in this case, will experience during the launch. Of course, the difficulty here is that these reverberant chambers are very expensive. There are only a few of them around the world. Basically, and you have to transport your satellite to these places, basically. So this direct field acoustic excitation offers an alternative to that. So you don't need to have a reverberant room. You just need to be lucky to want to test your satellite the week after Glastonbury, basically, because you're going to hire a lot of concert loudspeakers, put them in a room that you have, and with your satellite in the middle. So the purpose is the same. You want to replicate the same acoustic loading that the satellite is experiencing during launch. But of course, it's a little bit more difficult because you have to control these loudspeakers in a certain way. Yeah. Okay. Okay, so this is a little bit the context. And now, so how do we apply a digital twin here? So the idea was to do, to have a model, a digital twin of our tests in order to run virtual tests, but also to be able to see a full field acoustic, the full field acoustic pressure, let's say, in all the space around the satellite, because of course with the actual experimental test we only have a few sensors around that we can place, right? So the idea here that Alberto had in collaboration with the guys at the European Space Agency was to build first an electroacoustic model of the loudspeakers themselves. Then you actually place a lot of them all around your satellite in a digital environment, right? So you can see that in the second picture. And then you can generate basically all the boundary conditions. You generate the vibroacoustic environment in the simulation environment, let's say. So you apply your physical law that connects, let's say, your electroacoustic coupling, electromechanical coupling to the mechanical and acoustic coupling, let's say. And then when you start your tests at the beginning, you do a system identification. So with the system identification, what happens is that you measure experimentally your matrix of FRFs, right, between the inputs and the outputs. Our inputs are the voltages that we actually send to these loudspeakers, and our outputs are the actual measurements from the microphones, so pressures. And we use that to update the model that we have, our digital twin of the experiment. So we can update that digital twin in order to have an updated prediction, or not only at the physical sensors, but also at our virtual sensors, the sensors that we don't have in the physical experiments. So we use that also to correlate the model with the experiment. And then when we actually run the test, at the end, we can have a full field monitoring using these virtual channels. So that's the idea. Come on, why is not showing? It's showing the preview here, but strange. So can I just try to close and reopen maybe? I don't know why it's not. I just reopen the file. Too many pictures that are not working. Yeah, let's do like that. Yeah, sorry, it's not ideal, but you can see it in the small picture on the left. But in this preview, basically, you can see. I don't know why it's not showing on the right. It's, this one. I don't know why. We tried before, it was working, but yeah, of course, now it's the time that we need it. And yeah. Let me try another thing, sorry. I'll try to do it like this. Try to. Okay, we'll try to show it from here. Okay. That's working. Yeah. There we go. So what was I saying? Basically, here we created a small scale demonstrator for this application, and as you can see, we have a number of loudspeakers. There are actually 45, if I'm not wrong. So we have 9 columns of 5 speakers for each column. Each column is going to be driven by the same input voltage, let's say. So it's 5 speakers on the same column has got the same inputs. And we have a number of scattered microphones inside. And what we want to do is to achieve a diffuse field. So if we take, let's say at each microphone location, we take the let's say the pressures there, the statistical properties of each pressure measurement at each microphone location, so should be the same for every microphone. Let's say that's what we want to achieve for these tests. Of course, we have a lot of sensors, and during our experiments, what we want to do is not to use all of them in our feedback loop to update the drives, because it will be computationally too expensive. Basically, you end up with very big matrices to invert in a very short time, and it's practically impossible. So also what we want to do with this digital twin is to have a sort of a pre-test analysis, which is going to tell us what are the best candidates for control channels. So let's say that we decide out of, I don't know, 50 microphones that we have, we want to have only, I don't know, 20 that are control channels that we use actually in the feedback loop. And so this pre-test analysis is going to tell us which ones are the best. Yeah, here it's, so here is an indication on how we interact with this digital twin, let's say, in our product, which is called SimCenter 3D. Alberto has created an additional, I think it's called ribbon or tool here. It's called Adifan. And now the movie is very quick. Hopefully it works. But I will try to explain how it works. So basically at the beginning, you create your loudspeaker model here. It's mainly the geometry for now, because it's important, the surface of the loudspeaker and in order to understand the power that it's on the mechanical acoustic transduction. And then, of course, when you created your geometry for the loudspeaker, it can be also different ones. You create, you put them one on stack of the other, and then you create also all your vibroacoustic environments with the boundary conditions, etc. Now, what Alberto is doing is to create the environment for the microphones, so for the sensors. Of course, we have a digital twin, so we can create a lot of them, a lot of virtual sensors, which are then used to see the full field acoustic, the acoustic full field response. He also put a satellite in the middle, and we are able then, if we have a FEF model of that, we are able to see also the structural responses due to this acoustic excitation. Here, what he's going to do is to assign a lamp parameter model with the small parameters on each of these loudspeakers in order to take into account the electroacoustic conversion. And that's what he's doing. And here is assigning the drives, what we call the drives, so the input signals to the loudspeakers. Of course, we can have, we don't send the same signal to all the loudspeakers, but we can have multiple drives, right? As I said before, we had one for each column, for example. And here is where you assign them. And also you give a spectral, you give a target spectrum excitation at the beginning. Yeah, he's running this optimization. So basically it says, okay, I have a lot of microphones there. I want to optimize the control channels. So if it's going to say, run me this pre-test analysis, and if I give you like 20 microphones as candidate controls, which ones are the best? And here it says the control candidates, basically. It gives you which ones are the best. And here you can run also really a pre-test. So it's a simulation of the test, and you can see the full field acoustic response and also the structural response of the of your structure here. So if I move forward, so how does it work then during the actual test? We have created our digital twin. We can import that into our SimCenter test lab. And basically we run an experimental system identification. And with that, we can update our model. So we take into account, basically, we basically connect our physical sensor with the virtual sensor. So we need to have some virtual sensors that are placed at the same location of the physical sensors, such that we can update the model. With this model update, which is done here in the picture on the left, you can see a window. That is where basically this connection, this mapping is done. When you have this updated model, of course, you can run your experimental tests. And then at the end of the test, during the post-processing, you can see the complete view of the acoustic full field response. Okay, and here you have the comparison basically with and without the model update. So basically you have your simulation. Of course, it's not, your simulation model is not able to capture everything. So when you do the experimental system identification and you update the model, then of course your test is much more accurate. Okay, and this is what we are doing now for, let's say, with the same idea, but in the structural dynamics vibration application, let's say. So I show the acoustic side, and this is what I'm concentrating on in order to have basically the same type of digital twin interaction through our SimCenter software basically for a multi-input, multi-output vibration control application. So here in this case, we have a 3-axial shaker that is also used, for example, for qualification tests of satellites. As I said at the beginning, you have also these shock responses or random excitations on a satellite when, for example, it is released from the tower at the beginning of launch, or when you have stage separations, for example. So you also need to run these vibration tests. And here also we are creating this this similar environment that I showed for the acoustic application, also in this vibration application. So that's the end of my part, and now I let Claudio take the lead on the vehicle sound simulator. Claudio,
Good afternoon. Hello, and I hope that you can already hear me.
Yeah, we can hear you well. Yeah.
Thank you so much. And it's a pity that I cannot see you all, and thanks for allowing us to give this talk. Thanks to my colleague, and like Emilio say, I will be a bit the digital twin of myself speaking from Leuven. I propose that I share my screen if possible, given the technical issues that we are having. Perhaps it's going to be a bit more convenient. And I will then go on, and hopefully you see the screen I am sharing.
Yeah, you're all good.
You see that? That's all right. Thank you very much. Sorry. Okay, so I will try to compensate a little bit for the inconvenience, and I keep it a little bit shorter than the original 10 minutes. So from the satellites where we were, so from space, we land again and we go down onto Earth, and I will talk about an application in the frame of automotive. But first of all, as you see from the picture in the bottom here, I have to say that is not what I'm going to present is not at all limited to automotive, fortunately. But the examples that I will show on the other hand are focused on cars in my case. So I will talk about a technology that we call vehicle sound simulator. And the first question I will answer is why do we need to use digital twins according to the definition that Emilio gave in the frame of vehicle sound. Basically, to answer to those 3 questions, I will plot. So first of all, how does our mechatronic system sound? So to enable objective analysis about the current status of the physical twin as well as a digital prototype of it. How this could sound in terms of what if scenarios, and how do we make these modification happen in the design space of our object, and how we would like to sound, how it should sound. So how to set target and to comply with standards and requirements of all sorts. Basically, this is the reason why we resort to digital twin in the context of vehicle sound analysis and design. So what we really need actually is a technology that enables us to take the vehicle sound and distribute into components that are the main contributors to the full vehicle sound, both in the interior and in the exterior. And I will focus on the interior sound of cars in this case, like I was saying. And what I'm going to talk about is a technology that takes these sound features and encode them into a executable digital version of this vehicle sound. Why executable and digital? Well, digital is quite obvious because we translate these sound features into a database, but executable in the sense that we do not only want to replay this sound in a smart way, no, we want also to elaborate them, to really manipulate them, and like I said 1 minute ago, also to relate them to targets and to design variants. Then ultimately, we would like then, and I will talk about that, to couple this digital representation of the vehicle sound behavior with a digital representation of the vehicle performance in terms of powertrain performance and vehicle dynamics performance, in order to finally enable what we call live synthesis in free drive. I will give some examples of this, but I would like to make clear that although it looks like a gaming setting, and in fact it reuses many elements, like it was said in some calls this morning, so these can be also considered digital twin, but in fact what is the big difference is that in those cases where the real engines or engines for resynthesizing the sound are in fact very much closed in terms of box, so they are not editable at all. In this case, we open these boxes and in fact we make it an engineering tool. And what do we need in order to make it an engineering tool? In fact, I'm going to say that we need more than one executable digital twin. To do what? To enable a human, so a person, a decision maker, to derive decision according to an interaction with these digital twins. In fact, the typical use of the vehicle sound simulator technology is that a decision maker, it can be the manager of an OEM organization, it can be an MVH expert, sits on the digital, on the mock-up of the digital twin that we are going to drive, and operates through input-output devices similar to the one that would have on a car, in order to actuate a vehicle performance model that runs in real time in an edge device. This was explained in a nutshell also by Emilio, is a similar technology as the one described earlier for very different applications. What we really do is we input given quantities, we obtain in soft real time a computation through a chaining of different type of simulations in real time, and then we output a number of quantities that we make available for a parallel digital twin of what I was calling earlier NVH model. In other words, the model that enables to translate the vehicle state into the reliable and realistic vehicle sound. These type of models can be fed through experimental quantities, like I will also say in a description of a few use cases, and or with experimental, and or with numerical and simulated quantities coming from 3D, numerical simulation, CFD, computation, and also technology that resort to bench type of testing. So I was saying, in fact, that it is not actually a single digital twin that we are talking about. In fact, we are multiple of them, so digital twins. One of these, I will not repeat myself, takes care of the NVH performance. NVH, by the way, is an acronym that stands for noise, vibration, and harshness. For us, is the acronym that means the noise and vibration of a vehicle. And this digital twin, in fact, takes care of the encoding and representation of this type of performance all along the vehicle production and prototyping stage. From the early stage, virtual prototyping, up until the very late stage in which the vehicle is ready for being sold and sent to delivery. Then we have the vehicle performance model I was describing earlier, and I will tell also that this model does not only compute speed and rotational speed of the combustion or electric engines. No, it can also emulate, for example, the computer unit of the vehicle, control strategies, multi-physical attributes, and that's what we are. That's why we are leveraging it. There is also a third digital representation, which is the representation of the scenario itself, which is a visual landscape representation, just to have a more immersiveness. But actually, we have the ability of adopting a representation of another layer of reality, which is in fact the set of sensors that the vehicle itself has on board. And for example, in the era where we move towards autonomous driving, we have tools for emulating autonomous driving sensors such as LiDAR, radar, and so on and so forth. And we can make all part of this chain of digital twins. Now, to save a little bit of time, I will skip the video that you see there. It's quite a commercial video. You can imagine is representation of a typical use case of the vehicle sound simulator. And I will move to a number of use cases, and I will also skip one for keeping a bit the time. But I hope this will be representative enough and interesting for grasping why we use vehicle sound simulator technology in a flavor of digital version representation. The first use case goes as following. So it is from a commercial project, and actually we were asked to couple a detailed vehicle performance model, modeling also the ECU decision, so the brain of the vehicle, and the consumption and emission parameters of a vehicle under study is a plug-in electric hybrid, a plug-in hybrid vehicle, sorry. And we were asked to couple that with an MVH model, so really an executable digital twin of the sound of the same vehicle, in order to do two things. First of all, to match the existing vehicle MVH performance. So really, when an operator drives the digital vehicles, that it should behave as the physical vehicle. And secondly, also to enable the reproduction and realistic prediction of unmeasured scenarios, something that wasn't even measured or measurable in the first place. And that's actually, in a nutshell, one of the potential uses of this type of tools is that the OEM, the user, does have for prototyping and development purposes a digital twin in place, and the vehicle sound simulator hooks up onto that digital twin and enables a sound attribute quantification and qualification. By the way, this type of vehicle performance model are executed in the similar platform as described by Emilio, that is devoted to real-time operations. Here I have an overview of a couple of applications in which, instead of a full vehicle performance, we focus on a component of the vehicle in terms of performance. On the left side of the screen, you see a work that will be presented in an upcoming conference, in which we characterize on bench a tire, or I should say a set of tires, 4 tires, and then we virtually assemble them thanks to a technology that we call internally virtual prototype assembly, without the need of having a physical version of the full vehicle. You can imagine what is the power of it, is that you can imagine different assembly strategy, different type of tires per the same vehicle, or on the contrary, the same tire on different vehicles, and foresee and even listen to the effect of this assembly before the actual prototyping. And that's a bit what this work is about. The same goes for another component, very important in the area of electrification. In this study, we have focused on a gearbox. And in fact, here on the left side, you see the effects in terms of sound represented in this graphical fashion of a given gearbox design compared to an alternative gearbox design. With the same principle, we are able to act on our digital version, so on our executable digital twin, and replace virtually the gearbox and assess realistically what is the sound produced by the gearbox next, and also in combination with the all other contributors to the sound, so the background noise, the wind noise, the engine noise, electric or combustion engine noise. And this leads not only to a subjective assessment, but also, as you can see, to a set of measurable and objective quantification of this type of quantities in a fair comparison. Good. I will conclude with this slide by showing that, in fact, what we use the vehicle sound simulator for is to try to complement the physical world with the virtual world, and whatever is not yet available experimentally, we can in fact simulate in a number of ways with 3D simulation, 1D simulation, and we have interfaces in order to combine all of them into 2 digital twins, one that takes care of the vehicle performance, one that takes care of the sound performance of the vehicle. Here, this example also takes care of emulating and actuating another component that is a bit between the lines, which is the control strategy of the vehicle itself. For example, to obtain a given target in terms of speed or in terms of performance of the vehicle, or even actuating multiple motors on the same vehicle. Here, the example that I show is, for example, on activating the switching frequency of an electric motor. And after modeling this control strategy in a executable digital way, so in a way that by acting on physical quantities, one can alter the effects in a realistic way through the executable digital twin, one can also focus on the sound consequences of these effects. And in this case, for example, for those who are familiar with these control strategies, such as switching frequency of an electric machine can give rise to so-called pulse width modulation orders, which appear a bit in this fashion, like very high tonal components that, although very high in frequency, might also be audible and perceived as quite annoying because are very high and high pitch. So this study shows a little bit the power of it in a way that an engineer, an MVH engineer, can use this tool for balancing these quantity versus the rest of the vehicle sound in order to make this type of component not being an MVH or a noise problem for the design vehicle. And with this slide, like I said, I conclude my talk. I had a few other examples, but I would like to thank also my colleagues and the entire audience, and leave a little room for maybe some questions to my colleagues mainly. And thanks again for listening.
Thank you, Claudio, Emilio, and Mattia, for a wonderful presentation. A lot of very interesting results, even though some of them wouldn't load, but the ones that we did see were pretty nice. So I guess I can start off while people kind of think of questions. When you're talking about an executable digital twin, is that more of you're using the executable to access the information that's currently being stored, or is the executable always running in the background and you're just accessing it, or how's that kind of set up in terms of what an executable digital twin is compared to just a digital twin or data associated with the digital twin?
I don't know, it's difficult to coordinate with my colleagues. I can start maybe providing an answer, and then I will ask to Emilio and Mattia to fill in if possible. In fact, the question is quite relevant because I was very short on that aspect. I will resort a little bit on the definition that Emilio gave at the beginning, which was quite articulated. But what we define as an executable digital twin is, in fact, not only a model that we can actuate, like a static model that we can actuate and then we can obtain the result, but something that, first of all, can grow with along the design and development process. So it can be maintained in a way that since the early stage up until the very late stage of the design process is coherent with itself and also fully representative of that stage. And secondly, like also was mentioned by Emilio, it enables a two-way communication. So we can actuate the digital twin, and like you can see, for example, in this slide, the digital twins themselves either can interface with given protocols between each other, and or they can provide to a user possibility to interact in order to then be actuated. If I may say, and I conclude, what we are not really exploiting to the fullest with compared to the presentation of this morning, for example, is the entire IoT infrastructure that could be interfaced with our digital twins. So I didn't mention that, but for example, our real-time platforms can be accessed via web, and there are interfaces for it, and they can be run literally on a cloud. But for example, in my example here, this was not adopted, just to stay a bit, to be concise.
I think that covers
Okay.
what there's nothing more to say. So maybe just an additional point, the fact that we see them a bit running together. That's really the main idea behind it, is to have kind of an executable, so it's more kind of a black box that you continue to update.
Mhm.
Then it allows on the other end to get a few channels, measured channels, and physical channels to the link, and then allows to expand it to the full extent. Depends on, of course, how much reliable it is. It's
Okay.
But then it allows to expand it real time, quasi real time, to get more channels than the ones you're measuring microphones.
Yeah, the use of executable kind of threw me off.
That's a good point.
Yeah. Executable aspect of, well, something you execute, but now there's something that is evolving that's being executed continuously kind of threw off my understanding at the beginning. And I guess I didn't catch some of those points. Is there any other questions or comments from people, either virtually or?
If you can give us just a quick recap of what has been said, Matt, in the audience. I think Emilio probably about, because I kind of had the same question as you, Matt.
Okay.
Okay, so it's me and Michael. So while I've got Michael asking questions, so Emilio, from your show, quite often you were showing like a touch screen, like an iPad touch screen, or like pointing at the screen. Obviously that's great for like demos and what have you, but in practice.
You can't hear, sorry.
Yes, indeed. Sorry.
Okay, sorry. Can you hear that? Is that a bit better?
Yeah, now it's better.
It's also just me, isn't it? Yes.
It must be. They couldn't hear me either, so.
So my question is that something that's just designed for those kind of demonstrations, or would you have that replaced by something like a drone or some other kind of mechanism to deploy practice? So that was my question. And the question for Mattia was about the, obviously you're doing the acoustic excitation of the satellite, but there'll be vibration excitation as well, right? I guess you separate it deliberately. And I just wonder what the difference in sort of like amplitude of excitation for the structure was.
That's an excellent point. I mean, that's fully true. It's indeed mainly for kind of lab environment. So that's why it was indeed created for this robot arm to follow it up. Then we step further into the lab in GTTO. But that's not deployable on an offshore wind. In an offshore wind, that's a very big challenge. It looks like, I mean, it is a very nice eye catcher, and that allows them to see what we can also show with curves and plots and dynamic oscillations and so on. So that's something that we're working on right now, but there's not yet a plan to go and replace it with drones. That's also quite some challenges on the stability and so on. But I mean, a nice idea to go a step further and so on. That's not yet a plan.
Yeah, so yeah, correct. So we have standards to test both acoustic excitation and the vibration excitation. And it's true that in real life they are coupled, right? So they happen more or less at the same time. And instead we do industry tests separately. So they do first the acoustic test, secondly the vibration test. So in terms of amplitudes, I would say what we saw from the first slide. The acoustic depends a little bit on the launcher, of course, but it's about 130 up to, I think the maximum is 145 dB. It's quite low. And of course, it's not always a flat profile. We call it profile, but it's basically the spectrum of the excitation. It's not always flat. So that you have this maximum 145 more or less dB. But I think it represents a little bit of it's not always fully coupled. We say that it comes at the same time because, for example, the acoustic excitation you have it usually when you start flaring, basically the launcher. You have this big noise with the acoustic waves that go directly to the satellite and those are reflected through the tower. Instead, in terms of the dynamic vibration excitation, you have first when launcher is released from the tower. And second, you have this the shocks when you have the stage separations. So you know that you have these kind of exploding bolts that connect all the stages. And yeah, when these stages are released, shock type of excitation will go into the connection between the launcher and the satellite itself or the base. So that this type of shock. Also, there the amplitudes it really depends on the launcher and the satellite, etc. But yeah, we do tests also up to 10G RMS. Also, there depends. This type of shock excitation and also random excitation, because of course when it's traveling at high speed, you have also this more broader excitation over frequency. So yeah, they're both.
All right, are there any questions online that people have?
So perhaps I ask again about the executable. Did I understand well that the idea is to have everything behind a binary file? Or not?
You said everything behind binary?
Yeah, so everything like the binary file is just
yeah, yeah.
It's just the gateway to all of your work, let's say. Through that binary file, you can access everything you've done. Is that right? Or is there another? Because I couldn't quite hear the response in the audience, but so if you can, you know, say again about this executable.
Yes, indeed. I was also struggling to hear what was said in the room. So maybe if I may ask to my colleagues, Emilio, perhaps you have showed a slide in which you call it our definition of executable digital twin. Would it be possible for you to share it again, or?
Yes, sure.
I will then.
What I just mentioned before that you could not hear apparently was the fact that well, normally how we see the XDT, the executable, is that this run in parallel together with the test. So what I mentioned before was the fact that I mean we measure a few sensors for some data. We measure some data, and then at the same time, the exe file, let's call it simplified like this, runs together with the test, and then it allows to augment also the data through Kalman filtering, through other techniques, data-driven approaches, and so on. But that's also, it could also be seen like that augmentation taking into account the physics of the structure. So that's. I'm not sure what you mean by file. You mean just let's say input-output files, or if you can...
So is it something that runs somewhere in the background? I guess it's starting a process it's just starting a process, I suppose. But I wonder why it's called executable. It's just is it just the fact that it's an executable file is hinted by the fact that it's an executable
yeah,
file?
well, actually, that's a bit also commercial because this basically in many cases, like you can take the wind turbine example or the aerospace domain, there is quite some sensitivity on data. So normally with this executable, you can also think it like you have a very accurate FE model of a wing of an aircraft that Boeing is producing. And then this one is compacted, and then it's through this FMU format, which is behind this executable, it becomes like a black box. And then the other people, the people working on fuselage or on the gearbox, for example, in the case of a wind turbine, cannot access the FE. But the FE is fully accurate, it's very validated, and it's running in parallel. So this FE format is a kind of a standard which is used nowadays in the industry. and allows them to,
Thanks. That answered my question.
Okay.
Thank you.
Any other questions?
Sorry, Marco, that I didn't get it in the beginning. Apologies for that.
No, that was really good. It's interesting because it's kind of the opposite of what we are trying to do in academia side, but it's
True. Yes, indeed. If you put it in that way, that's.
I'm glad I came to this one because I don't know what Siemens and the industry are actually doing. So it's interesting to see this.
Maybe one comment on that, Marco. It's true. If you put it in this way, it seems like we want to make it everything, let's say, closed. And on the contrary, there you were pointing out the advantage of the opposite. But like Emilio was saying, in fact, that is a need when sometimes you have to interoperate with other entities. But you can map what many elements of your talk can map on the way we maintain our models. So also these are basically stored and maintained. Sorry, I have to use again the same word in a similar repository as a GitHub repository or GitLab repository. And in that sense, these can be wrapped and then pushed again on the digital twin execution. And it's not always needed to really compact them in an accessible way. But this being said, you're right. It sounded like too extreme of the same.
Thanks. No, yeah, okay. Thank you for that comment. And it's comforting. At the same time, though, I coming from the simulation side and perhaps uncertainty side, let's say being so sure about the data and the simulation is it's a bit it can be scary sometimes, maybe overconfidence about our own product and work. So, but again, I think I'm biased because I come from the uncertainty community. So, so I just give my angle. I let also other ask questions. I guess that was my comment. Thanks for the very interesting presentation. I really enjoyed it.
Thanks for the questions.
One more question out of the audience, and then we'll take a coffee break.
Yeah, thanks for your talk. It's really interesting. I was wondering when you're doing virtual sensing, if you tried applying your updated model to slightly different conditions. For example, if you've updated your model and the temperature changes, is your updated model still valid for the boundary conditions change?
Yeah, well, we didn't look yet at the temperature. Maybe this will be part of the discussion tomorrow. So I did, we are going to discuss about the PhD track, and then that one of the ideas could be to combine the temperature with mechanical vibration. But overall, on the boundary conditions, more in general, yes, that's what we skipped with that slide. Maybe I can show it. We have this is another. Again, another acquisition from Siemens. We got another really interesting tool to perform optimization studies, and it was somewhere here. Yeah, here it is. Mistake. Should not have done it. So yeah, all this tool what we did, yeah, cannot zoom in. Okay, we'll show it like this. So here we have kind of a classical updating procedure. So we changed the boundary conditions. So this blade was clamped before on a certain structure, then we rearranged it, and then we had to re-update the model because the boundary conditions and the modes in the frequency domain, they were completely different. And then we have now an automated process to do that through this KITS software. It's an optimization tool which then takes it as an input, the vibration modes from the test and from the simulation, and then does this optimization, optimizing parameters that we want. In this case, it was maybe see there on the clamping system. So there are some RBEs that's done to simulate the clamping, not as a perfect clamping, and then we were optimizing the stiffness there to do it. So that's we run this type of activities, sometimes changing boundary conditions and optimizing or changing the model. Then one of the ideas could be to do that continuously along the lifetime, meaning that you have this blade running for months, these fatigue cycles, and then you keep updating the model all along the test. That would be one of the ideas. Yeah, that's also another way to look at it. There are also studies in which we are planning to have indeed kind of a library, so FE models. For example, that's for damage detection. Now we're trying to envision how to identify damages. One of the ideas could be to have certain locations where it's more prone to get damages, and then we have different models, and then we pick the closest one to the real conditions measured by the measurement system.
All right, so let's thank our speakers one more time.